periodic in nature. If you look at the whole of this, there are just a few applications and maybe these shifting properties that we'll discuss. Right. 2, we'll look at Laplace transforms. Laplace transforms, those will take us some time, and there is a lot to do with that, how they are used to model highly volatile kind of phenomena. And when we deal with this, we may come up with some, we may cite some applications, and again we can see how a Laplace transform can be used to solve an ordinary differential equation. But please be mindful that what you did in ordinary differential equations should not be forgotten. Actually, you need to start revising what we did. Remember, I'm the same person who handled you there, so the nonsense of fooling around that we did not do this, that will not apply. I know it would have applied if it was another person who had taken this up, but now that it is me, the old guy, I know what I covered, and very many things are omit, and I say recall from what we did that this should be this. However much you will frown the face, I will request that you go and pick up those notes so you can see what is happening down here from around here. This is all directly associated with what we are actually from 2.7. From 2.7, 2.8, all the way up to 2.9. This is application of RLC circuits. You've already done some of these in, you have courses to do with the magnetism, you have courses to do with the analysis of AC circuits. You go into things like logic gates. You've done quite a number, I guess, already in some of those. I may not know the actual names of those exact courses, but all of this dwells on differential equations. So you can see solutions of ordinary by Laplace. So you must already know what an ordinary differential equation is. Solutions of homogeneous linear ordinary with constant coefficients. This one we did, but we are going to just incorporate a Laplace in there, and then we can see how it can also help in elucidating voltage fluctuations in circuit analysis, which I'm sure you've already done circuit analysis. Okay, that is the second one. The third one, you can see again, we are talking of ordinary differential equations. I'm going to start with this because I don't want you to forget what we did. I'll start with this. This one builds on exactly what we did. So you must remember what a differential equation is. And then when we talk of power series, this one also deals with some form of equations that are complex in nature, where you would have talked of expanding to a given function to power n. You can have an alternative kind of less strenuous technique that can help you solve that. So we are going to deal with this, and I'll start with theory. So in our lectures, we'll start with theory, this one here. We throw it out, maybe in 2-3 meetings, and then we'll continue. We have gamma and beta functions. So some of the distributions that are exhibited by some of the voltages that you will experience can be modeled using these gamma and the so-called beta or beta functions. So we will do some understanding of that. We have the Bessel functions, and here you will find that again these ones relate to differential equations and what we also call difference equations. So you can see ordinary differential equations solvable using the Bessel's equations. So some of these, then you can also have a Laplace transform of Bessel. Remember, we have Laplace in chapter 2 here, or the second topic. So it means that as we go through this, you make sure you don't forget. Otherwise, we have to deal with this. We have to do this in relation or in association with what will have been covered earlier. Okay, we have the legendary functions. These are also key in the analysis of fluctuations, and that should lead us to partial differential equations. Oh, this is another long kind of course, quite long. And exhausting it is quite tough. We will do our best. You can see it is given 20 contact hours. So we can classify. This is very key. That is the PDE. Usually I start with this one here. I usually prefer starting with those that are very bulky. This one is super bulky. For the group I handled last year, I started with this. And then I came to this one. You can see this one takes 10 hours here. So I started with the PDEs, and then I came to this one here, and I think we came to, this is the Laplace, right? Oh, yes, then I came to Laplace. Then we picked a few things there. Yeah, that was basically it. So we have the legendary and then the definition of a partial differential equation. So the order is going to be, we will start with the 3 because the 3 builds a lot on what we did. This one here, it's bulky, but the difference is, remember we had last time definition of an ordinary differential equation. So what is changing is the ordinary to partial. Why I started with this is that this one is a little bit related, not a little bit, it's actually heavily related. The applications may be very different, but there we are looking at full derivatives with respect to differential equations, but here we are looking at partial, we are looking at differential equations partially, and then we look at the different applications. So, and there are very many here. We'll pick and we'll go as far as we can go. But it's bulky. I will be lying if I tell you that all of this can be covered 100% with these virtual classes. Actually, it can, but it means you dwell much into the computations. As always, I mostly deal with the how rather than why, and then you help me out on the why. On the how, my responsibility is to dwell deep into the why, and of course for you students, you always do much to do with the how. The exam covers, I think, like 70% how, and there is some 30% why. If I give you an exam of 70% why and 30% how, you will see people getting retakes, and you even wonder whether they did engineering math 1. Okay. References, the references are very many. Some are not even here. There are actually some references out there that are better than even these ones that are cited here. So when we come to references, these are just tips of the iceberg. There are lots of online materials. In the generation we are in, you really don't have to spend money on buying a book. There are lots of free online resources and very rich in what we are doing. There are quite a number of YouTube videos that you can play. All you need is data, and then you satisfy yourself in terms of exposure. Okay, so I think there are no questions. If there are no questions, that's what we are going to look at, and we are going to get started now. I can only guess there are no questions. I'll just check what is happening in the chat room if there is anything useful. Someone asks whether they passed the math 2. I don't know whether you passed or you failed. You go talk to the head, Dr. Robina. She will tell you whether you passed or failed. That was Mr. Cheng Ronald. Just go to Madam Robina, the head. She will share the results with you. There is this Kamukuru, who is this Mulindwa guy. You see, I told you I was not familiar with Mulindwa, and someone is asking who the Mulindwa guy is. I wonder whether this one voted. I'm hoping Mulindwa did not just surface from anywhere. Never heard of him too. Very interesting. All right. Okay, I think those are the comments I see. The others seem to be just colloquials with much without anything that benefits the session. Okay, right. So I'm going to remove this screen and then I share another screen. Hopefully I still have you. Can I hear a present and then I continue just to make sure.
Present.
Yes, we are around.
Yes, teacher.
Present.
You can mute yourselves. You all sound like you are mourning the loss of someone, which is quite bizarre. But hopefully it is your networks that is making you sound like aliens. But that is not important. So let's get started, and I'll try to record the session. I had a guy who used to record these sessions last time. I don't know whether it was Caleb. Okay, so let me unshare this, and then I share a new page. Just give me a minute, please. Okay, all right, guys. Let me unshare this, and then I share a new screen. Okay. Okay. Can you guys see my screen?
Yes.
Okay. Good. Make sure everyone is comfortable as we move along, please. I'll not really restrict you from doing stuff during this session. By that, I mean, I'm not going to mute all of you because I would love anyone to unmute him or herself and ask if there is any burning question. And as always, you can utilize the chat if there are questions you have and you ask. I've seen quite a number of faces around the campus. I don't know what you're doing here because you must be at home, but for those who are on campus, don't come to the office to ask questions because you are not supposed to be here. So utilize this platform, and I'm also going to upload some of these materials on the Mwere so that those who can ask questions, you can always fire them via the Mwere platform of this course, and I can always attend to them. Otherwise, when we meet virtually, like on this platform, which is more interactive than the Mwere, I strongly encourage you to ask so that no one is left behind. Okay, power series solutions. Okay, this one, firstly, we are still going to start by solving. This should take us 10 hours, probably less, given that you're still fresh from what we've been just doing down there in year 2. Rather year 1 of engineering math 2. So when we talk of a power series solution, this is another form or approach that one could pick on based on what we did. You remember we looked at Abel's formula, we looked at the method of variation of parameters, we looked at a number of different categories. Besides the variation of parameters, there are also there were also other very many different forms of equations that we looked at, and for each method we looked at, we actually justified why we did that and why other approaches wouldn't work. Okay, let me just try to record this session. I need to record this. Record. Okay. I think. Just to make sure. Pause the recording. Okay, I think our session is being recorded. Let me just confirm. All right. So I recorded the session just in case people pick interest in reviewing these recordings. Okay. So what I was saying is that when we looked at those forms, there are other approaches we left out. That's why we are saying that one important and to approximate solutions of linear and then nonlinear equations with the constant Variable coefficients is the method of series solution. And we are saying no matter whether any solution is known or unknown, you can actually use this. So first of all, we want to understand the behavior of this. So we'll start with a quick review of what a power series is, and then we will dig deep into that before we start solving these equations. So first of all, let's try to understand a power series. If we have an equation, this is a series because you can see we keep summing. So you keep iterating A, you have A0, you have A1, you have A2, you go all the way up to AN. And then you have, this is, you have X minus X0. This is to the power 1 to the power 2. The power of X keep increasing, and the coefficients, that is the A0, as you iterate, because this can also be looked at in terms of a difference equation. It means if you have the whole of this, you can simplify its representation. The whole of this can be represented as a sum. So we can simply represent it as this here. That if you expand this here, you'll actually get what you have on the right-hand side, rather than the left-hand side. So if you substitute and you run from n equal to 0 to infinity, so it means when you throw in the first value of n, which is 0, this will be a0, which will be x minus x0, of course, to the power n. Since n is 0, this whole term here will disappear because it is to the power 0. You remain with the a0. And when you remain with the a0, that is this one here. Okay, then when you throw in n equal to 1, this will be a subscript 1, so this will be a1, then this will be to the power 1, which is just a1, x minus x0, which is this one here. Then when you take n to be 2, that will give you the a2 here, that will be a2 x minus x0, that will be a square, which is this term, and this whole thing can go to infinity. So this is this in red here is what we call a power series of x minus x0. Why a power series? You can see the x minus x0 is to the power n. So this can keep growing and growing and growing. And the behavior of this, if you incorporate what we call limit theory, and then the limit theory, of course, will be driven by the behavior of the problem or the properties of the problem you are trying to solve. So we are saying the numbers n0 up to an, those are coefficients of the powers, and the point x0 is what we call the center of the power series. This is the key here. As you go through this, please just don't leave any stone unturned. Anything here can be asked. So when you can be asked to explain or describe what a center of a power series is. So we are saying the x0 is called the center of the power series, and then the n0 up to an, those are the coefficients. And from 1, we are saying that it is a power series about a point x0. So everything will depend. And remember, the x0 is what you use to initialize. And a system, if you try to solve it, it must be initialized, because for whatever you are going to use it in terms of application, the question is, when does it start? When does it end? Are there jumps? Does it behave like a heaviside function? You can have something that behaves like this. So you find that you have jumps. and those jumps could constitute something. Of course, it depends on how you want to think of those jumps. So every time you have something like this, you realize nothing is going on there. So you have this. This is, of course, nothing happening because this is constant. You have that growth. This is constant. So any problem, this could be a problem that one may play with, and then you'll see the behavior of this X naught with respect to that kind of dynamics. But we'll dwell much into this when we go into applications. Okay, so we can continue, and then we dig deep into understanding these by categorizing them into what we'll call the radius of convergence. We'll understand what is analytic and then what is non-analytic. But given that we are still reviewing, we can now understand. We said the other one will be a power series about the point X naught, and we are saying the power series this converges at a specific point X1 if the limit as n approaches infinity. This should be smaller n because the n here is actually the infinity. If you remember what we did here, if you look at what is here, right. If you look at what you have here, so the n is infinity. So this should actually be smaller n going to infinity, where infinity can be quantified as that big N. So we are saying that we will say a power series, this one converges at a specific point X1 if the limit of this one here exists. Remember when I was telling you about the behavior of this, I told you we can use limit theory. And when you use limit theory is guided by the properties or the behavior of the problem or the system you are dealing with. Okay, so this is just generic. That's why I said you can use limit theory. Right. Then we say the value of this limit is called the sum of the series at point. You need to really, as you read through and you get this handout, to keep marking those. That is the sum of the series at that point. If the limit does not exist, then we will say that the series diverges. Remember, we say it converges if this limit exists. If this limit does not exist, we simply say it diverges. So if we go back to our one, which was given as, if we go back to one, which is given as this here, that is nx minus x naught to the n. This is the series. So we are saying given a power series, one, it is important to find all points x for which the series converges. And how is that done? It is done by simply computing the radius of convergence. We do it by computing what we call the radius of convergence of the power series. And how is that radius of convergence computed? There are two ways depending. So one, we are saying the radius of convergence of the power series, which is denoted as R, is given by this, which is the Rotator test for convergence. And this language we are using is part of real analysis. Now, some of this we are supposed to do in math too, but because I knew I'll have a review, now I'll get an opportunity to mention some of those here, and then we also do some examples. Okay, so this is part of real analysis, and we are saying this is when we talk of a root test, this is the limit as n approaches infinity. Then you have the nth root of the norm of that given sequence. This is a sequence, or R could be the limit as n approaches infinity over n over n plus 1. And this is the ratio test for convergence. We are going to do some examples on 2 and 3 in a short while. Before the end of this session, we'll have understood more of 2 and 3. Right. Then, so this is the radius of convergence. And remember, we said that when do we compute this? We basically compute this one if we want to establish the points or the would-be domain of the values that can be used. And for those values that are used, you want to know whether the series converges. Remember, if it converges, a limit exists. If it does not converge, then it means the limit does not exist. It may be continuous in nature, or it could be telescoping to infinity. We have what we call a telescoping kind of series. Right. So we are saying OR is equal to this, provided that the limit in 2 or 3 exists. You're going to say provided the limit in 2 and 3, they exist. Remember, why should we say they exist? It's because of convergence. If they don't exist, then convergence cannot be guaranteed. Then what about R being 0? R being 0, we are saying that series 1 converges only at the center x equal to x naught when we initialize. This is key. You need to distinguish the 3. So you have existence, which would be rather you have convergence, which would be existence of the limit. You have divergence, where the limit may not exist, and then R can be 0. If R is 0, we are saying convergence takes place at the center. And if R is positive infinity, then we'll say it converges for all values of x. Remember that domain of x is so wide. So if it takes on infinity, then it means you are protected everywhere. It is unbounded. Convergence is unbounded. That is this scenario here. Then if R lies between 0 and infinity, we conclude that it converges in this interval here for this less than R. Or you can look at this. Remember, this is a norm. It is plus minus. That one can be simplified to minus R plus x naught, which is less than here. You're basically targeting getting x in the middle. So if you target getting x in the middle, what will happen? Since this whole thing is less than the R, but remember this being less than the R, and it is a norm, it means you can have here positive and minus. So it's like you have a negative R here, which is less than this is sorry about that. This is less than the x minus x naught, and then this is less than the positive R. So since you want to take away, this is what you want to remain with the x in the middle, that one there. It means you have to add. Here you must add the x naught on either side, so that when you add the x naught here, this one cancels out. So you will have minus R. This will be plus x naught. This is less than. When you add the x naught here, you will only remain with the x, and then this will be less than the R plus x naught, which is actually this one here. That is the minus R plus x naught. That is if you remove that norm there. Remember, when you have x, this is the same as plus minus x. I think you know that very well. So you have either, so since this is less than that, you can take this on the other side, which is plus minus r. So if it is plus minus r, the minus, which is this one here, you'll have minus r here, then a positive r on the other side, which reduces to this. And we are saying it will diverge when this condition holds. And of course, you can do the same with respect to this, and you come up with an actual kind of range for this one here. Right. Okay. I think that is that. So we are saying the interval, if it will diverge, it diverges if x minus x naught is greater than r. So we are saying this is referred to as the interval of convergence. I've already told you must be familiar with all of these. So as you go through, I guess you'll do the needful. Okay. So this is just an example of the few things we've discussed here. So we can try to check out for 2 and 1. Does a limit exist? If it exists, then you can conclude it diverges. If it does not, we can conclude that rather, if it exists, we can conclude that it is the limit exists, converges. It doesn't, then it diverges. And we have looked at scenarios when it could be equal to 1 and when it will actually be equal to 0 and then positive infinity. So your computation, the answer you get to your computation actually guides the conclusion. So there are just some few basic examples here. For example, in this one here, you see we have n to the n, x to the n. So what is a? Remember, xn is our point of reference. So in this case, our an is n to the n, and you can compute. Remember, we said that for us to compute this, we can either use the root test, which is this one here. So since it is n to the power n, that suffices that we use the root test kind of limit to check whether that series converges or diverges. Okay, this one here, because you can see it is n to the n. That's why we are saying here we can take n to be n to the n. And if that is the case, we now cite this for the root test. Since the example there is to the power n, we cite this to here. That's what we are using here. Remember, we said it will be the limit as n approaches infinity of 1 over the nth root of an. But now it will be the nth root. Our an is n to the n, which will give us n. That is what we have here. That is r. It is the limit of that. Then if you have nth root of an, remember this is an. So what you have is you have the nth root of n to the n. If you compute this one should give you just the n. Remember, nth root, it means you have n to the n, and this whole thing is to the power 1 over n. This n will cancel with that one. If you consider towers of powers, then this will multiply that to remain with the n. That's why when you compute it, you end up with this one. This is the limit. This comes from that. But what is n? We are saying as n approaches infinity. That's what we said here in our definition. As n approaches what? Infinity. So if n approaches infinity, what do you end up with? Since it is 1 over n, 1 over something very big is basically 0. So 0 implies what? It implies that the limit exists, and since it exists, we say it converges for only x equal to 0. remember x keeps changing, and if we are y, remember this is x to the power n, but n runs from 1. So if n runs from 1, you have x to the 1, then you have x squared, x cubed. Yeah? Why? Because when you take n to the 0, this will be 0, and this will be 0. So this whole thing here will be 0. That's why in this particular case, n runs from 1. But you can see in this one, n runs from 0. You have to take time to understand this series here. Here, n runs from 0. If you have minus 1 to the power 0, and then you have x minus 1 to the 0, there is a way you can play with these ones here. But then the question is, if you had moved this one from 1, there is some information you may lose along the way. We are going to preempt this further. Okay. I think I can clear that for now. And then we continue. So we have example 2, that is the B, that is this one here. You have, this is now your AN again. AN is minus 1 to the N, then X minus 1, that is this one here. So since it is AN which is minus 1 to the N, again we'll use the root test, that is the limit of this, which is this one here. But remember, this whole thing is to the end, so you'll basically end up with -1, since this is minus 1 to the n. So when you end up with the -1, you have, this is 1 over, is this correct? What are we having? Okay, sorry, you have the norm. So if you take this, hopefully you've got it. Basically, you have root of the norm of -1 to the n. This is that, but remember this is the nth root. So this n will cancel with that one there. It doesn't matter. You could as well take this n out. You remember when we are discussing those things of what was it? Forces being solenoidal and being irrotational. We are dealing with these powers. I think you still remember when we are trying to check whether that energy can be conserved. So this n can still go out here. The property holds for it. So you have, this is -1 to the n, but you can have the norm, this is to the n, it will still be the same thing. And this whole thing is to the power over n. Then this n will cancel with this one. You remain with -1. And the norm of this is basically a positive 1 here, that one there, which is 1 over 1, which is 1. And we conclude that that one will converge for this. Remember, we said it is x minus x what? We said it is x minus x naught. Hopefully you remember what we did here. I'll just quickly refer you. That is here. X minus x naught. Is it greater than the r? Is it less than the r? Is it equal to r? So that is the situation we are looking at here. That was B. Yes, I think that is this part here. So we are saying convergence for all points of x in the interval x, that is -1. Remember, when you throw in your x naught, since you've got the limit, we said the limit at that point, just like in this previous one here, where we said that this is at x equal to 0, because we had established the limit as what? As 0. So at x equal to 0, that would be x minus 0, which would be x. But now this is at x, rather this is at 1, so x will be 1. Let's write it out here. X is equal to 1. So you have x minus 1, which is equal to 0. But remember, the 1 was the limit. So we have basically x minus 1 for your x naught. But remember, you're trying to relate it with the actual limit that you have. So if you have the norm, which is this one here, remember when it is minus 1, this is the norm, you have a plus minus 1. That is the minus 1 here. I have already demonstrated this in a more generic form. And then you have this one here. So when you simplify, you want only x. If you want only x here, this is minus 1, it means you have to add a positive 1. So when you add a positive 1 here, it gives you that 0. You add a positive 1 here, it gives you 2. Adding a positive 1 here, it will simply give you that x there. And if that is the case, of course, we are looking at conditions. If it is less than 1, this would be 2. And if it was greater, that is, if you compute this, we are saying it would diverge. If it diverges, that would be greater than 1. What would that give you? That would give you x less than 0 or x greater than 2. That is if you split up what you have here. Right. Okay. Where is my eraser? We have this. We'll continue. Then we have the third example. That is, if you look at the third example, this is x to the n, and this is over n factorial. So here we'll play with the factorial notation. Remember now, in this case, our an is 1 over n factorial, because this is our x to the n. So this is like x minus 0, this one here. In this case, this one was x minus 1, so our x naught was, I've been explaining this, that here x naught was 0. Let me just clarify a few things. I'm really hoping that you are following. By definition, we have x minus x naught to the n. If you remember our definition. Of course, I've not written the whole thing. I'm interested in this part, but just in case you are still trying to catch up with what I am doing, I am referring to this here. I'm referring to this right here. That you sum from n equal to 0 up to infinity, n of x minus x naught to the n. So for you to get x naught, this x naught, you simply have to compare with what is given. Because if x naught is 0, then you are going to remain with the x to the n. And this will be a n to the xn. So everything we are doing is based on this series here. Please be mindful of that. So if you follow what we are now doing here, in the previous example, remember in this one here, since it is x, maybe I can just write it somewhere here so that we make a quick reference to it and the people don't get lost along the way. Remember, we have the sum as n moves from 0 to infinity. And this is a n. This is x minus x naught to the power n. So whatever we've been doing here is basically based on this. For some of you who are silent, because I'm not hearing questions. So an, when we say an is n to the n, this an is basically that one there. But now what is this one here? Here in this case, the x naught is 0. Why is it 0? Since this is x minus x indicator that the x naught is 0. From this, you can tell that x naught is 0. So you remain with just the xn. For this example here, I've already demonstrated down there that the x naught is 1. Why? You can see it is x minus x naught, but when you compare this with what we have in our general form of the series, which is this one, you can see that your x naught here is 1. That is the x naught being 1. But remember, when we computed the limit of this, again, we got it as 1. That's why we got x minus 1. Then we took the norm and we say if this is less than 1. The 1 here is the limit we got. This one here is the limit we have established. But what is this? This one here is what we have picked from here, the value of x naught. Then when it comes to this still takes the same. So you can see here xn over this one, but remember this is an. So it means that our an will simply be 1 over n factorial. That will be the an. But what is x naught? According to C, x naught will be 0. Because this is x minus x to the n. So if x naught is 0, you simply remain with the xn. Okay. That is the C. We are saying here, that is this part here. I wanted to keep the question in the neighborhood, but I'm losing it. Okay. So for part C, maybe I'll just write this whole thing. This is xn over n. So C is given as x to the n over n factorial. So since that's what we have, that is this part here. We are saying if n is this, but remember, we said you can either use the root test or the ratio test. So here in this case, we use the ratio test. Just to go back briefly in our definition. Here, we said if R is equal to this, you can use the root test, and if it is of that form, you can use the ratio test. So in this case, under C, since the question given here, this question here, since this is a ratio, we can now use the ratio test. So if you use the ratio test, the question is, what do you come up with? We do a similar thing, a little bit related to what we've been doing. So here we are saying here an is 1 over n factorial. And if that is the case, we will have an, this is by definition. This first part here is by definition. That is an over an plus 1. So what does that mean? So if we have an, it means an plus 1. When you add 1 here, you add 1 here. I think that is quite obvious. No one should get lost. So we have an, by definition, it is given by this. That is from the question. Then what about an plus 1? We add the 1 here, we add the 1 here. That is the 1 over n factorial, then over 1 over n plus 1 factorial. But then the question is, how does this reduce to this one here? For that to come to that, we have okay, what we have is 1 over n factorial. And we are dividing this by 1 over n plus 1. This is factorial. But since this is a division, we can take this one up. So what would this become? This would actually become n plus 1. This is factorial. This whole thing is over n factorial. Now, there is one beautiful thing about this factorial notation. You know that if you have n factorial, this is the same as n into n minus 1. You can expand it, and you can even say n minus 2. You could still go up to n minus 3. If you want to exhaust it here, then you put there factorial. This is the same as that. So since this is n plus 1 factorial, we can expand the numerator until we get something similar to what we have in the denominator, and then we settle it there. So it means that if we are to do this, we can have our n plus 1 factorial. What is this? This is the same as n plus 1. Then this is into n plus 1 minus 1. We can add this factorial notation there. But what does that give? Since this is n plus 1 minus 1, remember what I have just stated here. It means this is n alone, so we will remain with n plus 1, then into n factorial. The balance here without factorial notation mark. But remember, this whole thing, according to this one here, it is divided by n factorial. Since this is n factorial, this will be cancelled with this one. You only remain with the n plus 1. And the n plus 1 you remain with is what you see here. That is the n plus 1. Since this is n plus 1, when you compute the limit of this, if n is infinity, then the whole limit here will go to infinity. And since it is infinity, we conclude that it converges for all x since r is infinity. Remember this conclusion, we have already discussed it. We mentioned earlier here, where up here. Yeah, we said that, you see that? We said that if R is infinity, this is called the interval convergence of the series. Why? Because we said if it is infinity, actually it will converge for all x. That is to beef up the statement that we have. I think it is basically this one. Okay, it is here. We said that if R is positive infinity, it converges for all x. And since it converges for all x, then we drew this conclusion that this is called the interval of convergence for that series that we have. Okay, I don't know whether they are. Okay, let me first continue.
Question.
Questions?
The denominator.
Yes, okay.
The denominator on that ratio, the part C that we have done.
The denominator is what?
Like I'm failing to understand how the one went into the factorial part. Because I thought it is.
How the one went into the factorial part? Where? Which part are you now? Okay. Sorry? Part C.
Like the denominator is an plus 1, where an is 1 over n factorial.
Mm-hmm.
Like when you add 1 over n factorial plus 1.
No. Please just repeat that. Repeat that. I think I missed you somewhere. Go on.
Okay, the denominator of the
When you
ratio.
spoke of the denominator, you are referring to this one I've highlighted, right?
Yes. Yes. Like when you add 1 over n factorial to 1, do you get like what we have here?
No. You are mixing it up. Let me just probably clarify a little bit. What we have, young man, what we have, what is given is we have a n, which is 1 over n factorial. Here it's like you're dealing with what we call relations from what we call difference equations. But since this one we are adding 1, we are looking at what we would call forward shifts. So here we are saying if an is equal to 1 over n factorial, then what is a n plus 1? That is the question. Since this is the an, then it means we add a 1 here, and then you just add a 1 there. So it means it would be 1 over n plus 1. Then again, this whole thing, factorial. I think this is the question you're trying to ask. How the 1 got inside there. Is that the question?
Yes, sir. I've understood.
Yes. We are picking it from here. We start with this one here. Is that okay?
Yes.
These are just relations. These are called relations. So if we have n, which is 1 over n factorial, then the question is, if we move forward, these are like time steps. We are saying you are here. So if you move 1 step forward, it means you are going to this one here. So from here to here, if you add the 1 here, this is moving forward. That is a shift. So if it is a shift, depending on where you are positioned, then we are saying if initially this was 1 over n, then what would be an plus 1? An plus 1 would be 1 over n plus 1. You add again a 1 here. If this one was n plus 3, then we would still add a 3 here. It would be n plus 3. Are we together, okay?
Yes, sir. Thank you.
Okay. Hopefully there are no other questions. I insist if there are other questions. Some of you up to now, you are still shy. You lack a confidence. You think when you ask, people will say that guy always never understands. My friend, you all have your destinies. Always feel confident and comfortable to ask. This is a university, and you should never shy away from anyone, especially when you are dealing with the academic related work. So for those who may be having questions, you can always throw them into the chat. I can always put people there. For now, I think there is nothing in the chat. Right. I think I can clear this. I don't want people to ask questions when I've cleared these things, because it would mean 1, to repeat everything, or 2, to ignore what you have asked, so that we don't waste the time again rewriting what I've already written. But since there are no questions, I think I can clear that. And we look at D. Okay. D is here. So you can see for D, if you compare with our general equation, x naught is 2. Our x naught is 2. And you can also see that here, we have to use what we call our, again, ratio test. Why? If not D, this is F, sorry. We are here in D. D is 2n over n factorial. And this is x minus 1. I think I can rush through these ones. So since this is minus 1, x naught is 1. Then what is our an? And our an, this is 2 to the n, and then you have over n factorial. So we bring in our ratio test, which is this one here. So in this case, we are saying an is the term you have. Our an is our an now is this one here. Our an is the whole of that. Then remember, by definition of that power series solution, this is x minus 1 to the n. So the minus 1, remember by definition it is minus x naught, so x naught is 1, then to the power n. So since this is a ratio, here we'll use the ratio test. And when you go ahead to use the ratio test, don't forget this, because I'm going to scroll down now. What we will get is what we have here now. This is our part D. Okay. So from our part D, we have an, which is 2n over n factorial. Now, by definition of a ratio test, by the way, when we write this here, when we write this, Lucy Nisima, you better mute yourself. Okay, so we have when we have this is simply being picked from our definition up there of the ratio test. I don't want people to forget where we are getting that. We have it in our definition. This is 3 here. We are picking that from here. So since D is given by an is given by 2n over n factorial, by definition, remember we have an over n plus 1. So we simply follow the same procedure we used in the previous one. Since an is this, then an plus 1, because we need to substitute the denominator. An plus 1 will be 2 to the n plus 1. We add the 1 there. I think Mr. Cheng, you are now with me. This is exactly what we did. Then in the denominator, you also add 1. So how do you simplify this? This is an over an plus 1. So we have an, which is 2. This is 2n. I need to clear this a little bit. Errors. Okay. So what we have is 2 to the n. This is over n factorial. And we are dividing this by the whole of this. But remember, dividing by this is equivalent to taking the reciprocal of that. So it means this is times, this is n plus 1. This is n plus 1. And the whole thing is over 2. This is over 2 to the power n plus 1. Okay, we are going to simplify this a little bit. How? Remember now the n plus 1, our n plus 1 is the same as, of course, this is with the factorial. This n plus 1 is n plus 1 into brackets. Then this is into n plus 1 minus 1. Again, factorial here. So this will be cancelled with this. Then it will give you n plus 1 n factorial. So it means this will be 2n into, I'll have n plus 1, then n factorial. This will be n plus 1, and this is n factorial. Then this is over, this is n factorial. We can split these two down here. Remember, these are powers. When you have the base is the same, you can add the powers. That is So that means that this one you can have it as 2 to the n times 2 to the 1. This is multiplication here. The base is the same, we can add the powers. That is the 2 to the n plus 1. So since we've split up this by using the rules of indices, that is 2 to the n times 2 to the 1, it means this 2 to the n can cancel with the other one. So we can cancel the 2 to the n cancels with this 2 to the n. I think we are clear there. Then we have n factorial cancelling with the n factorial. What do you remain with? You remain with the n plus 1. This whole thing over 2. That is what you are getting here. That's why we are saying that the whole of this is this one here. That is the n plus 1 over 2. And once you have this n plus 1 over 2, we want to compute the limit. I think you know how we compute the limit of this. So since this is the only n here, you throw the limit. This will give you infinity over 2. You have something very big, extremely big, you're dividing it by 2, that will give you infinity. I'm hoping you still remember your engineering math 1. You did some limit theory in engineering math 1. You have something very, very big. You are dividing it by something very small. It remains something very big. Or you get a small car and you try to load it with something very big, with a big car, then that small car will disappear into the big one. Basically, we are saying if you have 1 million and you are dividing it with 1 shilling, if you have 1 million and you are dividing with 1 shilling, you are going to get 1 shilling. Rather, you are going to get 1 million. So this is infinity over 2. Infinity over 2 will give you infinity. And we are saying the series converges everywhere since R is infinity. The conclusion for this is the same as the conclusion we had there. Right, I think I can now throw in some speed. I guess things are now very clear to everyone. Okay, the same applies now to these ones. These ones you can now go and you do yourselves. So you have these ones, this is E. You can see what you have in E is here, it is a ratio. So our AN is N over N plus 1. You can see the part of here, the X naught is 0. You can see what you have. So if you deal with that and you come in E here, that can come out very fast. So you have AN, which is the N over N plus 1. And since we are using the ratio test, you can go ahead and compute the AN plus 1 by definition, because this is what we use. That will be the AN plus 1 over N plus 2. Then you have this. Remember, you divide by AN, so you take the reciprocal of that. That is the N plus 2 over N plus 1. That gives you this thing here. And once it gives you this thing, you have this one here. I think you guys, you still remember this. This one, the way you arrive at this, you have to be a little bit careful. I'll try to go, this is more of limit theory. How do you get the analytic solutions of that? I'll just do this very fast. So try to expand this. If you try to expand this, what will this one give you? This one will give you N squared. This will give you N squared. This one here, the numerator, N squared plus 2N. This will be plus 2N. Then when you expand the one down, this one here, that will give you N squared. Then this is plus 2N. This is plus 2N. And this is plus what? Plus 1. That is what you will get. So what we do in limit theory here, you divide by the one with the highest power. So it means you'll divide by N squared. You divide the numerator and the denominator by N squared. What will that give you? It will give you 1 plus, this will be 2 over n. This will be 2 over n. Then this whole thing is divided by 1. This is plus 2 over n. This is plus 1 over n squared. And of course, here you're computing the limit. This is the limit as n goes to infinity over the whole of this thing here. But sure, when you take n to infinity, this will be 0, this is 0, this is 0. So this will basically, if you throw in the limit, this will give you 1 plus 0. This is, I think, your engineering math 1 plus 0, then plus 0. These are zeros. So you have 1 over 1, which is 1. And that is the answer we have got here. So that's how you arrive at this one here. Okay, and since it is 1, then we can draw conclusions. That's where we are saying that. And so the series converges if x is less than 1, and it will diverge if it is greater than 1. So if that is the case, you can now say, since this is 1, why do we say x? Remember, in the question, I'm hoping you know when, because when it is a, okay, when you come to D, is it D? Sorry, E. Remember the x naught is 0, so you remain with only x. Remember we said it is the norm of x minus x naught. So since it is the norm of x minus x naught, you only have this one here. Where is it? That is this one here. Since it is this greater than that, it means here you have plus minus negative 1 when you remove this here. And that would give you this one here. So it lies between minus 1 and 1. And we said when x lies between 0 and the positive infinity, we do conclusions. So since this one is less than 1, you have to do it for both. If it is less than 1, it will diverge, and if it is greater than 1, it will, if it is less than 1, it will converge, and if it is greater than 1, it will diverge. Okay, I think this other one, we don't have to go into it. This is f, which is n squared x minus 2. This one, you can also deal with it in terms of this one you can use the so-called ratio test, that is an. This one you could as well. Okay, since this is this and this, you don't have there. Okay, so if you consider f, you have an, which is n to the 3. Is it n to the 3? Okay, that is n to the 3. And then you have n plus 1 would be n plus 1 cubed. So you have n cubed over 1 plus n plus 1 cubed. And then when you go ahead, you can come up with those conclusions. Right. That one can lead you to these ones here. You can now go and you try out all of these. You have number 1 all the way up to number 12. Okay. Are there questions? Hopefully you are still on.
Sir.
Yes, Mr. Alonso. Alonso.
Like now the examples, like example F. First, when I supposed to use that, because on the question they are like summation from n to 1 up to.
Example F.
Yes. Yeah.
Yes.
When I supposed to use like that one, like summation from n to equals 1 up to infinity.
No. If you are summing, you can sum from anywhere. But sometimes the nature of the function you have may not be good for some of the functions you are dealing with. So in this case, you're starting from 1. You get me? Because here, depending on these examples here, these are mostly illustrative. We are not applying them to anything. But when we start solving the differential equations using these, you'll see that we can have constant shifts of these n. You start with n equal to 0, but you may find that if n remains zero, then you can redefine. So in this case, this is n. Here there is really 0. If n was 0, this would be 0. Then that would be given that this is n here. If you have 0 to the 3, that is not something very good. Is that okay? I think you still remember your. I think you still remember your calculus. Hopefully, you still remember your calculus. When we say 0 to the power 0, you cannot conclude. If you have 0 to the power 3, you cannot conclude with this one here. Let me just do it right up here. So this one is obvious why we are taking it from 1. Because if n is 0, you have 0 to the power 3. So what is 0 to the power 3? What would this one give you? Hey, the one I was talking to. Was it Mr. Alonzi? 0 to the power 3 gives you Mr. Molindo, the new coordinator. Whatever you say, we'll go with that. Since you are the new representative, Molindo or Raymond, 0 to the power 3 would give you what? Molindo. The new coordinator.
0.
0 to the power 0. Okay, Mr. Molindo says 0. You have to be very careful with that. These are some unique cases, and you can see even here in the first one here. We are taking n to be 1 because here, if n is 0, you would have a very interesting scenario of 0 to the power 0. You know, Molindo will give you that fake answer that it is 0. There you have to dwell much into that kind of analysis. This would not make a sense in any way. What you get as 0 is any number to the power 0, not 0. By any number, here you're dealing with the natural numbers. 0 is not part of those ones. You can go to infinity. That can be 0. Infinity to the power 0, it can give you a 0. But 0 to the power 1 or 0 to the power 0, this is not necessarily 0. You have to, you remember those other methods you discussed. There are very many other methods that come into play in this kind of analysis. When you have situations such as those, when you're into real analysis, you've had the Rotator, having infinity to the power infinity. This is the same situation here. So since here we are starting from 1 because you have n to the n. You don't want a scenario where this n is 0 and then you have 0 to the 0. That would be bogus. The same applies to this one here. If you start from 0, if n runs from 0, you will have 0 to the power 3. This is a situation here. That is another bogus one. But here we don't have to mind because we know that 0 factorial is 1. So this one remains defined. Then what about this one? Also it is defined. So here, these ones, we can take them from 1. Is that okay? But for the other one, we cannot do it that way. And the reasons I have just told you that would be a little bit amorphous. So when you throw your 0 and you power it will give you 0. But in terms of real analysis, that does not imply that. 0 to the power 1 is not the same. When you say, you think of it this way, when you say 0 to the power 3, and you say this is the same as 3 to the power 0. Let me just clear this. Where is this? All right. It's like you're saying 0 to the power 3 is the same as 3 to the power 0. If you remember, I don't know who handled you in English. I think it was Mr. Hassan Kayondo who handled you in engineering math 1. You must have done quite much in terms of limit theory. But, and we are going to bump into these situations more. But anyway, to summarize what you are asking, when do you start with n is equal to 1? I've cited the scenarios. Scenarios like 0 to the power 3, those would be logical. So that's why here we jump and we go to n is equal to 1. Yes, this is in Namunguba. Is it? I hope I'm pronouncing the name. Maron. You have your hand up. Your question.
Yeah, and it's not a question, but you said any number to the power 0 is being 0, but it's 1.
Any number to the power, any number to the power. You are right, mister, you are right. That was Selipe. 3 to the power 0 is 1. Carry on.
And a 0 to the power n number, I think 0.
Yes, it is 0, of course, but I am saying, when I say it's bogus, first of all, when you have 0 here, if n is 0 to the 3, this is going to give you 0. This whole series disappears. But does it mean that this series is 0? No. That's what I am saying, that you cannot take this, because when you say you are summing, this is a representation of something. A series is derived from a sequence. So if this is a sequence, you cannot sum a sequence and you say a sequence like this one simply goes to 0 during the initialization process. That's why we cannot run from n equal to 1. That's why I'm saying that if you have 0 to the 3 for this one here, this would be bogus, because in reality, if you have, of course, in terms of applications, like if you talk of work done and you sum up with respect to your beginning point to the end point, they'll tell you that the work done is 0. But if you look at it, that is if you're just looking at it in terms of work done. But if you look at other activities involved in moving around that closed path, you'll find very many non-zeros. We are saying work done is 0, but you've actually lost calories. This is what I am trying to say. You are sweating. It's like these people who go in a gym and they run on a treadmill. If you compute the work done by someone running on a treadmill, it is 0. But the gadget is reading that the person has lost over 30 calories. So the same applies when we say we are summing, and the sum is in the initial phase. It's like you have a number line, you move from here, and you are at this point here. You've not moved, and then you say you are summing. So what are you summing when you are at that point? That's why I'm saying this would be illogical. This would be bogus to say you are running from n equal to 0, because when it is a series, it means you're moving in some kind of step. Is that okay? And the step is discrete in nature. That's why we sum. Because if it is continuous in nature, then we will be integrating like that. But in this case, if you are here and you keep at that, and you say this is 0, then it means you've remained at that spot. Then this whole sum, this term here, wouldn't make a sense, because it is not a sum of anything. So yes, it is 0, but in terms of applicability, if you are here and you say you are summing what is here when you've not moved, it does not make a sense. That's what I am saying. I don't know whether I am clear.
Yes, you're clear.
Am I clear, guys?
You're clear, doctor.
Okay, thanks, Maron. Okay, there are some questions in the hierarchy. Why did we use the ratio for party F? Okay, I will answer that. You could, by the way, like for party F, you could even use the other version. I think this is still, okay, this is another person, Raymond. I know Raymond, what he's saying, because for the ratio, we were having something over something. Okay, I'm going to get back to that one. Let me first see. Sheila, I thought a number to the power 0. Okay, that one we have rectified. Are we really gonna start? Okay, I think that is probably that old post. All right. Okay. I think this was Emron. Emron, was it Emron? I think he's asking about this part here. That's why the ratio test here. So for him, since this is, of course, one thing by definition of what we have done, one would probably go for the root test. But remember, when you go for the root test, we have the nth root. This would be the nth root of, this is what? This is n to the 3. You can use this, you can arrive at the same conclusion when you try to use this here, but it will be a little bit more demanding, because when you take the nth root of this one, you're going to have 3 over n. So you're going to have n to the 3 over n. If I'm with you, Mr. Emron, is it Emron? But here, since we have an, so the nth root, there are even some ratios where this root test, by the way, could work. Because I could have something like maybe 1 over, say, n to the n. Then you may ask, why am I using the ratio test here? So I could still use, since this is n to the n, I can borrow from the root test, though this could as well be the ratio test. So in this case, because of the cumbersomeness that may be associated with this one, remember when you have n to the 3 over n, this expansion here is going to call for methods like that binomial expansion, and then surface very well. Maybe you may have to think of Taylor expansion to deal with that 3 over n. But since we have the definition of the ratio test, which is an over an plus 1, and we don't have, and we already have our an, which is n plus, sorry, which is n to the 3. Then for a scenario like this, we could use either of the 2. I don't know whether I'm clear there. Mr. Emron. Emron, I don't know whether he's a girl or a boy. Abel Matovo. Emron, are you still with me?
Clear.
Abel, yes, what's your question?
Yes.
Matovo. Matova, I can't hear you. Probably you should go in the chat and you type your question. I think your network is a little bit shallow. Okay, I think we can continue for now. Let's, yes, you are there, Matova? Oh, okay. I think you've sent your question in the chat. Let me see what he's saying. Where is Matova? This is the non. Okay, the power thing has an error. About which power thing? Matov says the power thing has an error. I don't know which part. Matov, I wish you could direct me. Which power thing?
like the one you say n power n power n. There must be a
Which number are you talking about? Number?
The part A.
I really can't hear you clearly. I'm trying to figure out what you're asking. Over which power thing? Are you on E? You are on F? I don't know where you are exactly. Huh? The power thing. I don't know whether you're on F. So we have n to the 3, and then we have n plus 1 to the 3. So if you have that, this thing you are going to expand it. I don't know whether you are here. Are you here, Mr. Matovu? Huh? Okay, I wish you could direct me more. Sorry? Okay, what we will do, I know the problem you could be facing with respect to referring me to. I'm going to share these materials. Once you have the materials, it will be easier for you to point me to where the mesh is by simply saying on page this. But now that you don't have the notes, you are probably struggling to direct me. But I thought you are probably still referring to F here. But it seems you're not referring to F. I wish you could just tell me, is it A, is it B? Maybe I start from here. We have A up to F. I don't know which of, this is now Arena Itwe. Arena Itwe, you can erase those things you have put. Oh, I help you. Right. I think someone had a question. I wanted to peep into the chat room. I saw some longer questions that I was trying to make sense of. This is, let me first go back to the chat. Okay. Oh, okay. Abel says, let me first work on Mr. Matov here. The power, okay. N power n is not equal to 1 over n power n. N power n is not equal to 1 over n power n. What is this? Did I mention that? You are saying that n power n is not equal to 1 over n power n. Yes, I agree with you, Mr. Matov. I think I agree with what you're saying. You are saying that n power n is not equal to 1 over n power n. You are saying it is not equal to 1 over n power n. I think I'm just trying to, this is what you've written, Mr. Matov, and I agree with you. This is not this, because n power n, this one here gives you 1. This would give you, is this one? This will give you n over n to the power n. But this is n to the power n. I don't know why we are picking this, but I agree with you.
He's saying from part A.
Sorry?
He's saying for part A, so you check part A.
But part A, we used the root test, I think. This is the root test. The root test, the denominator is the nth root. This is the nth root of a to the n. This is a to the n. So if it is nth root of an, what is an? An is n to the n. Then the nth root. But what is n to the n? This is nth root. This is n to the power n. Then the whole thing to the power 1 over n. I think here we agree. If this is nth root is 1 over n. But now here you are multiplying the powers. N times 1 over n is 1. This whole thing here is simply n. I don't know whether this is where he is. I think you agree with me that that is correct. If I have the nth root of n to the n,
Yes,
that
it's
would
correct.
be, yes. So if he's referring to this, maybe there is some misunderstanding. Okay, I will go to, there was a question I had picked interest in, though I had not read it clearly. This was from Lindsay. This Lindsay, I have failed to understand this. Is this a girl or a boy? The other one is Kamukama. Lindsay, can you talk to me?
He's a boy.
He's a boy.
Yeah.
Okay. And is the name pronounced like that, Lindsay, or it is my already pronunciation that makes things sound a little bit off?
It's Lindsay.
Sorry?
Lindsay.
Lindsay.
Yeah.
Hey. But are you the one who is pronouncing the name? Are you the owner of the name? I wish the owner of the name would pronounce. Okay.
Sir, it is Lindsay. It is Lindsay.
It's
Lindsay.
Lindsay. Okay. Thanks for clarifying the pronunciation. Okay, I'm trying to look through your question. You are saying the terminologies you are using, I don't know which terminologies are these. You are saying they are fascinating. Are they more of application? And if so, which one in particular? To be honest, you say you understand what we mean by work done is zero, but not specifically to this concept. Also discrete in nature. All of those, all of those I beg. Okay, maybe those are the terminology. Well, I think I've said very many things. But when we say we are summing, it means you're dealing with some kind of a discrete data set. I think this one is obvious. Meaning the time interval you have, or the time step, or the steps you have. You guys, I'm sure you have been doing some programming. So here, if you sum, it means the steps you're dealing with are manageable in terms of summing. Like if you're moving on a number line, this one. This means if you have 1, you have 2, you have 3, these are discrete in nature, you can actually sum these ones up. But what if you're looking at an interval, you have a step, you are moving, for example, from 0.01. You could be moving from 0.01 up to let me say 0.2. And here you are moving in time steps of 0.001. Surely this is not discrete. Maybe I need to clarify. I know if you have to program and you write this as a time step, where there you go, you have this one here. So you're moving from this, there is a 0 here. You are moving from 0.01 to 0.02. And the times or the interval in between, it may not necessarily be time, it is 0.001. So you get the difference here, you divide by that. That should give you how big the steps are in that case. And if you do that quick analysis, what does that give? Doesn't that give you something like, you have 0.01, that is 0.01 when you take the difference between those two, and then you divide it by 0.001. That should give you around 10 steps, I think, if I'm not mistaken. So the interval is already small, and you are even moving into smaller time steps or intervals. So this one here, you can't use this one here to deal with that. This one you'll have to deal with something continuous. I think what Lindsay, if I go to the pronunciation right, was trying to refer to that whole thing of 0 to the 3. When I said this one would be bogus in the beginning, I said when you're summing here and if n is 0, it means if you're at this spot here, you are going to remain there, if this is the scenario. Because here you are dealing with a sequence, and because this number line here, this could constitute a sequence, 1, 2, 3, 4. And if it is a sequence, then if I am at a point n here, I may want to understand what is in between here. Then I may sum up, which is this one here. If I sum and the data set I'm dealing with is discrete in nature, I'll sum. Otherwise, if it is continuous, I'll look at the integral from probably point A to point B. Or I can sum from point A, which may be 0, to point B, which is infinity, over the function that gives me that. But since it is discrete in nature, I simply sum from n will equal to 0 to n being infinity. Linz, I don't know whether that clarifies what you are trying to ask. Mr. Kamukuru. Are we somewhere? Or you are getting, okay. Hopefully you're not getting more lost. All right. I think I'll answer one more question I had. This is Mr. Wafula. What is Wafula saying? Is there a very good chance of landing on a question that requires approach using any of the methods? This man is joking around. Of course, I don't understand what you mean by that. And you are saying even in a generic nature. What are you saying? Wafula, can you say something? I would love to hear what you are saying. What you have written doesn't make a sense to me. But I think here you are saying it doesn't have to be a good chance. Why does it have to be a good chance? Landing on a question that requires that. Mr. Wafula, if you're not there, I can continue. I've not really made a lot of sense in what you had posted, but if you can, you could talk and I get to know what you are trying to insinuate, really want to understand. Otherwise, I didn't really get you. Okay.
Okay. Excuse me. Okay, my question was, can we get like a question that requires using any of the approaches?
I lost you somewhere. Can we get a what?
Can like a single question from this, whereby I can use any of the approaches to solve, whether I use a root test or I use ratio test and I get the same thing.
Yes, though this thing you call a thingy, I don't like that type of English, but where I think it is your generational kind of talk. But Mr. Wafula, it's not about the questions. It's about how you apply the things out there in the field. Once you graduate and you become an engineer civil, it's not going to be about questioning papers and answering questions, but your comprehension of this content and the way you are going to apply it. You are in undergrad and you could end up anywhere. You may continue and probably you become even an electronic engineer if you so wish. So it's about the application. When you say you use this kind of a test, what does it imply with respect to a would-be function that may look complex in nature? Then when you are programming and you are writing some algorithm that is going to be used to help solve a problem, or it is an algorithm that is kind of generic, but in that generic nature, you can make it specific with conditions. It means you cannot write that algorithm if the functions you are dealing with are rational in nature, or they take on that root form. So it's not about a question you are going to be asked in the exam or the test. No. But of course, those questions can come. But I don't want you to understand this in terms of cram or answer the question and pass. No, that is wrong. That would be a very poor mentality. It should be the why. How can this be used in your area of engineering? And the applications are so many. That's why I'm even starting with it. So good chance, yes, it doesn't even have, the chances are very high that you will bump into this one. In terms of applications, they are extremely many. It depends on how you unpack your mindset and you accommodate how the things can be used. Okay. Hopefully,
all right, thanks.
Hopefully we are together, Mr. Wafula.
Yes, we are.
All right. Okay. There are questions here. You guys, you can go and you discuss them. They are all yours. All of these are yours here. There is find the radius of that. Then there is the next one. There is an exercise here. All of these are for you to do and you appease yourselves. Oh, it is a buffet of very many things. Okay, so I think next time I'm going to share these materials with your coordinators, and I'm yet to upload some of these things on Mwere, where you go and you enroll yourselves. I'll just share the enrollment key with you. Okay, these are just exercises. I think when we meet next, as soon as I get another slot from Dr. Robin Akolabako, we should be able to pick it up from here. Let me see if I can get a session tomorrow. I needed to finish this a little bit faster, but I think we are now, you have set pace. So we'll pick it up from here to probably tomorrow. I'll see if I can get a session tomorrow. And then we meet and we continue. So I'm going to share the materials and we'll be starting with some definitions of analytic and non-analytic functions. And we get to know what ordinary points are vis-a-vis singular points. These are based on the equations that we have been looking at. And once we have a clear understanding of that, we will now start off with the actual power series solutions about ordinary points after understanding what an ordinary point is. And this is going to take us into some messy kind of analysis that we will do. All right, I think let's end it there, unless if there is a question. If there is no question, I'm going to end the session here. Questions? All questions? No questions. Okay, enjoy your lunch. Let's close it here for now. A good day. Are you there? Are you there? Sonia and Mulindwa, are you there?
Yes, sir. A good day to you. Yes, sir. A good day to you.
Why did you take so long to reply? I think you had dozed off. All right. So I will communicate with the coordinators. I'll coordinate, I'll communicate to Mulindwa and Sonia when we'll be having our next session. And then I'm going to send these notes. I've not yet uploaded them on Mwere, but I'm going to send them to your coordinators. And the coordinators will share the notes with you, probably on WhatsApp or emails. Hopefully you have also group mail. I'm going to share these with your coordinators. Okay, a good day, guys. Enjoy your lunch and stay safe. Bye.